Throughout your time studying statistics, you've come across lots of different distributions. For example, you've come across a normal distribution. Let's just say normal 100, 15 squared, which is distribution of IQ in a human population. You've also met things like binomials. So you could have a binomial with 20 trials and a probability of success of 0.4. What we're going to look at here is when we take a sample of several readings. So for example, if we were taking 5 readings from this sample, you might get, and you can generate these with your class pad, you might get something like 5, 7, 7, 9. And I said 5, didn't I? And then you might get a 10, say. What we're going to be looking at in this section is what happens when we calculate the mean of this sample of 5 and then consider how the samples of size 5, the means of those samples, how they themselves are distributed. Would it be another binomial? As it happens, it will turn out that when you take means and then you took another sample of 5 and you calculate the mean of that, and another sample of 5 and take the mean of that, and if you were to do that over millions and millions of samples, you'll actually find that they turn out to be normally distributed. That's the means. The individual values over here we know are binomially distributed, but the means themselves are normally distributed. And we're going to look at how that works with an investigation, which we'll do in several parts. I've worked through this investigation and we're going to go through my answers. You can always do it yourself, and you're going to find, if you do, that you're going to get different answers because just the whole idea of statistical sampling. And maybe we'll look at a bit of that as well as to how these samples could vary. Obviously, if you take a very large number of samples, like millions and millions, you're going to get less variation. But if you take, as we're going to do in this investigation, 6 or 25 or something like that, you're going to get a very different picture to the person sitting next to you in class. So over here, what I have are, and we're going to use this later, 72 car prices. Now, these are not genuinely from a car lot. I got ChatGPT to write them for me. I gave it some instructions about how I'd like them to be distributed, and it produced this list for me. The lowest car price here is $3,000 over here. The highest one is $12,950. So when we look at the range of car prices, let's say we were to produce a box plot, and we know that with a box plot, I'm not saying that's an accurate box plot for this data, but we know that the range is the entire length of the box plot. I managed to spell range as rage there. And that would therefore go from 3,000 at this end up to 12,950 at this end. And so that would be the range. Start thinking about taking samples from this, even if we just took a sample of 3 cars. So even if we ended up with the 12,950 and the next 2 highest, I'm not exactly sure what they are, there's a 12,250 there, and the only other, there's another 12,950, so there's 2 12,950s. But if we took the 3 of those and took their mean, it would be less than 12,950. So immediately, even though I've taken a very biased sample of taking the 3 highest values I could see, the range would be reduced. And if you think about a random sample from these, which is unlikely to contain those 3 cars, it's going to be smaller still. And the same thing happens at the other end. If we biased our sample by taking the lowest ones I can see, and I'm not going to spend ages looking for them, I can see a 3,500 there and a 3,650 there. You may be able to spot some that are actually smaller, or there is a second 3,000, so let's include that one there. But if you take the mean of those, it's going to be more than 3,000. So immediately we're reducing the range when we look at the distribution of the samples of size 3. And obviously with larger samples, you're going to be forced to take ones that are further away from 3,000 at the bottom or 12,950 at the top. And so what's going to happen is these things are going to actually tend towards the middle. And so that introduces the idea of something that we're going to talk about called the central limit theorem, or CLT. And we'll go through this in more detail. Hopefully that you did understand that little introductory bit, but let's go through our introduction to the central limit theorem. Statistics is the science of variability. If everyone and everything were perfectly identical, everybody was the same height, the same weight, and so on, there would be no need for statistics. We could draw conclusions from a single observation. We only need to measure one person and we know everything about everybody. However, variability is everywhere. Car prices, exam scores, fish lengths, or even daily temperatures. This variability means we must analyse samples to make predictions about the entire populations. That is, unless the population is something very easy, like the marbles in a jar you have, where you could literally take measurements about every single one of them, and then you wouldn't need to use statistics because you'd have information about the entire population. One of the most powerful concepts in statistics is the central limit theorem, CLT. The CLT provides a remarkable insight. Regardless of how data is distributed in a population, the distribution of sample means will become approximately normal or bell-shaped, we know the normal distribution from our methods course, as the sample size increases. This idea is the foundation of much of modern statistics and is why we can make reliable inferences from sample data. Let's just think about that for a moment. It doesn't matter what distribution the stuff comes from. It could come from the distribution of cars that we talked about. It could come from a binomial. Strictly speaking, if the underlying data is already normal, then we're not using the central limit theorem, but that's not a distinction we make in this course. And there's other distributions, like uniform distribution and so on, both continuous and discrete uniform distribution. So beyond this course, there's lots and lots more distributions. And then there's just the sort of random distribution that we had over here with the data that I produced from ChatGPT. That doesn't follow binomial or normal or anything like that. I did ask ChatGPT to randomize a bit between certain values, skewing it in a certain direction and so on. So it's just sort of any old data. But even so, if we take these means of samples, they're going to become normal. It's a very powerful idea if you think about it. So key ideas: populations and samples. A population is the complete set of data we are interested in, e.g. the heights of all students in a school. A sample is a subset of the population, selected to represent the whole, and there's a whole science behind that, which I'm sure you've discussed elsewhere. Sample means. The mean of a sample gives us an estimate of the population mean. If we repeatedly take samples, and that's the whole idea here, and calculate their means, those sample means themselves form a distribution. And I've given the game away by saying it's going to be a normal distribution. The importance of random sampling. For the central limit theorem to work, and this is important because this could be an exam question, samples must be selected randomly from the population. That is easily something that they could ask you for 1 mark in a test or an exam, so make sure you know that one. Random sampling means every individual in the population has an equal chance of being included in the sample. This ensures the sample is representative and eliminates bias. In fact, it doesn't really eliminate bias. You could still get a biased sample, but it's a step towards eliminating bias. For example, when drawing cards in our activity, and I realise this is an activity we haven't done, but if you draw cards from an unshuffled deck, you can predict the order you're getting them in. The whole point is here that we will be selecting cards at random from a deck. Shuffling the deck thoroughly before each draw ensures randomness, and it needs to be thoroughly shuffled. And you'll probably know that if you played any card games at all, including things like Uno, where things tend to congregate when you play. The central limit theorem. No matter the original shape of the population distribution, uniform, skewed or otherwise, and we've talked about this a bit earlier, the distribution of sample means becomes more normal as the sample size increases. And this is part of what we're going to be investigating. As the sample size increases, I talked about taking samples of 3 cards here. That won't tend to be normal very quickly at all. So what would happen is we would need a bigger sample taken randomly, and the bigger the sample, the more quickly it will tend to a normal distribution. So the sample size is a big factor, again worth remembering because it's easily asked in an exam and just a 1-mark answer. The mean of the sample means will approximate the population mean. So whatever the original distribution looks like, so it might be a really skewed distribution like this with a mean over here, when we do the sample means it will tend to be normal and the mean will be at the same place. The standard deviation of the sample means, or the standard error, decreases as the sample size grows, making the sample mean a more precise estimate. We talked about this up here when we talked about the fact that when we take samples, those samples won't be at the extremes, they'll move towards the middle. Why does this matter? The central limit theorem allows us to make predictions and calculate probabilities about sample statistics, even if the original data is not normally distributed. It underpins techniques like confidence intervals, see later, and hypothesis testing, which are essential tools for decision making in fields as diverse as business, science, and education.